My doctoral degree is in pharmacology, but that's not why I'm teaching you this stuff. As you progress in your chosen field in the health sciences, it's important to understand how molecules work together to create certain types of responses within the body, as well as how drugs work. And so we're going to be looking at that. Most people think of pharmacology and they automatically assume drugs, but it's also important to realize that, while drugs are certainly pharmacology, this also applies to molecules in the body that are not artificial, that are not introduced from the outside. Endogenous ligands or substrates. These are molecules that then are produced by the body, they're found in the body, they're a naturally occurring molecule. And these endogenous ligands, it's important to understand that they have very important functions, and pharmacology can help us to understand how they work. The exogenous molecules are molecules that are administered from the outside. These are molecules given from an external source. They could be molecules that are normally found in the body. For example, insulin is something that is normally produced by the body. But in individuals who are diabetic, for example, they might not be able to produce that insulin, and so will need to receive it through injections. Now, a drug is usually considered a man-made substance, or, for that matter, an herbal remedy or some type of natural substance that has a measurable or physiological effect on the living system. People have sometimes make the assumption that natural, as in, those herbal remedies are somehow better. And they often forget to mention those herbal remedies when they talk to their doctor. And unfortunately, some of those herbal remedies can interact with medication that might be given. And so we can see sometimes dangerous interactions that occur because people just assume that natural means there's no effect. Or no, let me say, no negative effect, no negative side effects. Emphasis here then on physiological effect. It needs to be something we can measure, something we can compare through a placebo-controlled group, and so forth. A ligand or substrate that docks to a protein is, in a way, or in itself, a chemical reaction. If you think of chemical reactions, normally we're used to dealing with small molecules. Molecule A plus molecule B equals molecule C, or however you'd like to write those chemical reactions. And in this case, though, if we consider molecule A as being our ligand and molecule B as being our protein, the product becomes this new complex of ligand and protein. And as a consequence of this, if we look at this as a chemical reaction, then we can actually look at the kinetics of the reaction the same as we would with a chemical reaction. The chemical reactions, if they're going to proceed forward, they need to be energetically favorable. Alternatively, there needs to be a source of energy invested into that chemical reaction. Many chemical reactions are reversible, and this includes the ligand-protein interactions. In fact, it's very common for the ligand to associate and then detach, and then associate and then detach. And so we get this back and forth that occurs. This process is concentration dependent. The higher the concentration, the more likely we are to have a protein bound with the ligand. And that brings us to the vocabulary word of affinity. Affinity is the rate of the association. So it's essentially the backwards and forward. It's the rate for this association, this formation of the protein complex. But that's a little bit tricky to understand, so we can put it in layman's terms as thinking about affinity as how tightly a molecule binds another molecule. And so it's a little bit of a silly analogy, but superglue would certainly be considered to have a high affinity, whereas saran wrap, which never actually works, I hate saran wrap, has a low affinity. It just doesn't stick very well. The molecules with a high affinity spend more time associated to the protein or the DNA molecule or the large molecule that it docks at. Whereas if we have low affinity, then we would likely see more of it as being free in solution. Affinity is measured by comparing the amount of ligand that is bound to the larger molecule, usually a protein. And so we create what is known as a binding curve, which is shown here on the left. A binding curve, often this is shown in log. In this particular example, it's not in logarithm, but many times it is shown in log, where what we do, if I were actually conducting this experiment in the lab, what I would do is set up several different reactions, and I would use maybe a very low concentration, let's say 1 nanomolar, then I'd use a little bit higher, I'd have maybe 10 nanomolar, and continue to, so I'd have several different reactions. Each of these would be its own reaction, so I'd do it with my 10 nanomolar, and I would measure how much of my molecule is bound, and that would give me a data point, like so. And then I'd have to do the experiment again using 20, and that would give me a data set like so. And then of course 30, and so on and so forth. And then what we do is we actually, so this one would have to give me data set right there, and maybe I'd do something like 0.5 and get a data set right here. And then we do a best fit curve. This would be a little calculus. I'm not going to get into exactly how you would do that. Honestly, I don't know. I plug it into my computer and let the computer do the work for me. So a high affinity, what we would see is at very low concentrations, we have a fairly good amount of that ligand bound to the larger protein. Whereas at low affinity, if we compare this low affinity molecule, you can see that, you know, we only have about, what is it, probably about 30%, a little bit less, bound to the protein. Now, with affinity, we sometimes see what is known as competition, and that can occur if we were to put 2 molecules or more in the same solution. So I'm going to dump 2 different molecules into my beaker, and I'm going to compare how the molecule binds to the protein. If the competition, the other molecule, is going to bind to the same binding site, then what we end up seeing is a change in how much molecule binds. So this would be what's normal, this top line here. So this is my normal amount. So if I look 10 nanomolar, then usually I get about whatever that value is. So let's say 75%. But if I put in a competing molecule that binds to the same protein in the binding site, then what I end up seeing is a change. So I'm still looking at ligand A. Ligand A is the one I'm measuring, but I have another ligand floating in solution, this ligand B. And so what it does is it essentially knocks some of ligand A off its perch, so to speak. And so we end up seeing a change in the affinity, change in the percent binding. But importantly, the actual affinity doesn't change. Affinity is considered a property of the molecule-protein interaction. And so the value that we use to measure affinity doesn't actually change. Related to affinity is the saturation curve. So this involves binding, and it looks at when the ligand concentration becomes high enough that all of the binding sites are occupied on the target molecule. And again, we would use a binding curve to measure that. So we would actually look at this curve. We would plot this on our graph with a variety of different data points, you know, here and here and here, and then do a line of best fit, something like that. The Bmax, okay, if we were to extrapolate and follow this out, eventually, it would take a while, eventually we're going to hit that Bmax, at least in theory. Usually we don't really see us hitting the Bmax, although it does depend on affinity. But once we're here, we consider the protein to be saturated, where we start to level off there. So if I were to ask you on the exam, I would say anything between here would be counted as saturation, at least to me. Now Bmax is the maximum percentage of ligand at saturation. Again, not usually 100%, but often very close. Hemoglobin, for example, has a very high affinity, or has a high affinity for oxygen, and hemoglobin saturation at most equals 98, maybe 99%. Now this KD has a special definition, and it is an important term to remember, and it's the concentration required to occupy 50% of the binding sites. And when we use KD to compare the affinity of different molecules. So a molecule with a lower KD a smaller KD is a higher affinity molecule. And so we might compare molecule, let's say molecule A and molecule B, and maybe they bind the exact same receptor or the exact same enzyme. Molecule A has a KD of 10 nanomolar, where molecule B has a KD of 100 nanomolar. In that case, then molecule, whoops, that's not what I meant to do. In that case, molecule A would be the higher affinity molecule.